We have Mark Laban, Sam Evangelista, and Sean Allman. We'll be talking to you for about an hour today. We're starting off with Mark talking about one of the types of invisible problems, at least the solution to an invisible problem, which is pipelining. And then Sean and Sam will go through a presentation. So Mark is probably going to be talking about 10 minutes, and then Sam, Sean will go through about 40 minutes. We'll have time for questions at the end, and you're also free to ask questions during the presentation itself. So, Mark?
Good morning, everybody. So I'm here today to talk about invisible and visible issues in high-rise buildings. Pinhole leak is an invisible problem that buildings have, but only for a short period of time. It becomes visible once the water is starting to drip down on somebody's head. Then it's a visible problem. So you know what pinholes are. I want to explain real quick how pinholes happen. So in 99.9% of the case, the pinhole leak is from a hot water pipe. Why? Hot water in a high-rise building needs to travel long ways in order to get to every floor, and in the meantime it cools down on the way. So excuse me. So they came up with a solution to have a recirculating system that collects the water. Once it's fed all the units, it collects again on an express riser and gets back sent up on the way to the boiler to reheat and then sent on the way. So it's a circle. That circle is going on 24/7, 365. The flow of the water, the velocity of the water is what causes erosion. So it literally, the water chips away of the inside wall of the copper pipe until you have a pinhole leak. The cold water doesn't do that because cold water is stagnant in the pipe. It doesn't move. It only moves once you use the water, but when you stop the water, it doesn't move anymore. So you have 99.9% of pinhole leaks are from the hot water pipe. These are no accidents. That's a disease. It's something that you can, there's three ways really to go about pinhole leaks. You can call a plumber, and you can have him come by and replace a section of pipe. That is a patchwork. This is not that's not a real solution, because when the plumber goes away, the next day it could happen that there is just a few inches above where he fixed the pipe, there is another pinhole leak, because the whole system is affected by erosion. It's not just a little section. So the real solution here is patching is really just a solution. It's a good solution for the plumber because he has to come back more often, more frequently. There is another way. It's repiping a building. That means you call a plumbing company. They rip out all the existing copper pipes. So that means they have to cut holes in each unit. They rip out all the copper pipe and they install new copper pipes. This is a good solution. The problem with that is it's very intrusive. There's dust. There's all the drywall dust, and there's fiberglass from the insulation, and then you need to patch the holes back up. Then you need to paint or drywall and put tiles back on. So it's very intrusive. It takes a long time, and usually residents are not very happy that plumbing company is in and out for 5 business days, or even more, until everything is really completed. And there's a third way of going about this. This is the least intrusive one. It's pipelining. The existing hot water system stays in place, even though it's eroded. It stays in place, and it is being lined. So that means instead of ripping it out, the water will be drained, and there will be the pipe will be cleaned with hot compressed air, and if needed also sandblasted to get rid of all the built-up that's inside the pipes. Once the pipe is clean, a batch of epoxy is mixed. It's a 2-component epoxy that is designed just for that solution, and will be pushed through the pipe on one end until it comes out the other end. This epoxy will dry overnight, and in the morning the water will be turned back on, and you have a new pipe within the old pipe, basically. It's basically a plastic pipe within the old copper system. Now, pipelining is the least intrusive one, and it also is the fastest one. So you have probably 20% less cost, and you also don't have the headache of it being such a big project. It's way quicker, we're way faster than repiping the system. So now I finally got the slide. The slides will just explain the process, really what it is. I'm not sure if I can get this going here. 1 second.
Can we get your presentation up?
Oh, thanks. If we can find it, it's also not a big problem. We're outside where you can see, where I can explain the real process of pipelining. I can explain it in detail outside if you're interested in how it really works, the whole thing. So that was short and crisp for me. This is it. And if you have any questions, please go ahead.
Thank you. Good enough, for instance, rather than cutting pipes, to have, say, one of the vanities open, and is air pushed through so that the vapor comes all the way through the system, or how do you actually get this epoxy to go through all of the copper?
When we start lining, the epoxy is traveling about 4 to 6 floors per shot, per injection. So let's say on the 6th floor, you have to, underneath the vanity, like you said, we'll take off the supply lines to your sink, and we inject in there through the other 8 floor or the other 4 floors until it comes out on the top. So it's not one shot continuously, it is step by step. Depending on the size of the building, it's step by step, every 4 floors to every 6 floors, depending on the diameter of the pipe and the size of the building. So we do have to go into the units, and we also have to cut the pipe in order to inject every 4 floors. But other than that, there is no intrusion. The nice thing about pipelining is that residents hardly even notice that we're there. There is a manifold that's being installed for the time being that needs to be installed on every floor. Other than that, there is no dust, there's no tools, there's nothing within the apartment, which is a great advantage.
So Mark, your slides are up now. Why don't you go through your slides if you want to, and then we'll come back to questions.
Sure, okay. So this was the recirculating system that I was trying to explain. This is a typical building layout where the hot water up top is the tank, and the hot water is distributing on a main header on the top floor, and then it goes down and feeds all the units, all kitchens, bathrooms. And at the end, on the lower floor, the hot water collects again and gets pushed back up, or pulled back up actually, back into the boiler room where the water gets reheated and sent on the way. So you can see this is a circle, and the water is constantly moving. And the problem with that is that especially the smaller diameter pipes. So a building has, on top it has bigger pipes, and the riser, as it goes down, as it goes further, it gets smaller. The smaller diameter of pipe is the one where the pinholes usually start. The reason for that is the same amount of water, the same volume of water has to go through a half-inch pipe to the small pipe as goes through the top. So the velocity is much higher on a small diameter of pipe than in big ones. But that being said, the erosion only starts on the smaller pipes, but it keeps going up. If you keep waiting and keep patching the pinhole leaks, you will run into more issues along the way. And the pinholes are starting to get bigger faster just because the thickness of the wall thickness of the pipe is constantly decreasing to a point where you could, technically, we've seen it before, where you could pinch the pipe with your thumb. So this is the recirculating system. And this is the pitting that I was talking about. This is how erosion looks like. We have pipe samples outside also that you can actually take a look at this. It's not an even, erosion is not even. It's water creates turbulences within the pipe, and so some areas are affected more than others. This is the velocity of the water, and also poor workmanship in some cases, which also affects the cold water. If something is being soldered or has been soldered, a connection, you need acid in order for the solder process to work properly. This acid has to be usually wiped off. Sometimes it doesn't get wiped off, so it stays there. And it is an acid, so it corrodes the pipe from outside in. So that's why poor workmanship is also a factor. It's not as bad as the velocity of the pipe. That's the major cause number one for pinhole leaks. This is the process created. Here you see the hot compressed air, how we clean the pipes and how the pipe is being heated up for the process. The epoxy needs a certain temperature to react properly. Then the air is being pushed through the pipe, so it's always going from the small diameter to the big diameter where the epoxy is applied. So the epoxy gets pushed through on one end, on the bottom in this case, until it comes out on the top. That way it is ensured that everything is 100% coated. After the coating is done, there is a 45 minutes running time in order to make sure that the epoxy is tacky enough to stick without any air. Then the air will be shut off, and the next morning the water will be turned on, and you have a new pipe within the old pipe. The warranty, compared to a new copper pipe, this warranty is much longer. The warranty for Ricoh's is 25 years on line pipes. Of new copper pipe, you get probably like 2 years maybe. So there are issues when there's, for example, galvanized pipes in some buildings, in really old buildings. Those pipes need to be replaced. Lining is just not, it doesn't make sense. It would cost too much because galvanized pipes, they start rusting. In order to get the rust out, it takes double the amount of time than it would be lining copper pipes. So I would always suggest 100% if there is rust in pipe, if you have rusty pipes, if you have galvanized pipes, they need to be replaced into copper pipes. Or these days, PEX pipes, plastic pipes are big these days as well. So, and the warranty is much better as well. Now that's it. Thank you very much.
Let me just, in terms of administration, we'll just finish off with a question that we had, and then we'll go through the rest of the presentation, then we'll come back to any other questions at the end, just to make sure we have time to cover up everything.
Absolutely.
So do you have any further comments? Okay, thanks. So, Sean and Sam, you want to go next?
Yeah, thank you. Should we switch? Sure. Yeah, I need to switch the presentation.
Close that, and you go down to PowerPoint. You can pull up yours. And you just have to go to slideshow.
There we go. Good morning. Obviously, I don't make these things for tall people up here, so I'm going to have to bend over a little bit. Can everybody hear me okay? My voice tends to fade off a little bit. Good. Okay, we're going to talk a little bit today about when we first started the session, we started talking about visible and invisible problems. That was the title that was posted outside. We kind of changed it because we thought that might be a little bit boring because the visible stuff is obviously apparent. And so the idea today is to talk about some stuff that's not visibly apparent. So it's the stuff that you might have a tendency to walk past, you might not notice it, And so I'm going to show you some examples of stuff that I've had the opportunity of walking through and seeing in my career. So I've just to give, I think you've read the bios probably. I have the opportunity of looking at hundreds, and I've probably looked at thousands of buildings in my career doing physical due diligence. And so I get the opportunity to look at entire buildings right across the country from top to bottom and see lots of neat things. And a lot of the stuff that we see also gets investigated. So if we see issues where we think there might be a problem, we also get to do some investigations. And we also work in a company where we are doing investigations. So we see the sort of full gamut of stuff, which is really cool. What I want to do is start off with just a little backdrop, a little overview of some of the primary causes, like some of the big picture things that we see which cause deterioration. And then just go through a bunch of examples. And John asked me to get to some meat. He said you guys are really anxious to get some good content, so I want to move through a whole bunch of examples that I've seen that they thought might be useful to you. And so we'll just work our way through those. I've got a ton of examples. I'm going to move fairly quickly. It might be beneficial if you see something that really piques your interest, you want to ask a question, you might want to just ask it along the way. I'm fine with that. Just stick your hand up. And then we'll just try and finish it off with some just a little bit of a wrap up and some preventive measures. And so I like to start off with this graph because this is a graph showing the total value of building permits across Canada. But what it's really showing is a trend in buildings. And you can see there were some building peaks, obviously, back in 1989, and then as recent as just before 2008 and peaking again in 2014. Like the value of building permits that are being issued is huge. But what it's telling us is that the building stock is growing astronomically. Like the building stock is continuing to grow. We are not demolishing those big buildings that were built back in the 60s and 70s. They're continuing to be maintained. And so we're dealing with a building stock that is not only getting bigger and bigger and bigger, it's getting older and older and older. And for anybody that's involved with buildings, you know that the sort of typical, like a theoretical, if you will, lifespan for a lot of building components is around 25 years. And so if you go back to 1989, I'm not sure if you can see I think I lost my laser pointer, but the sort of 1989 cutoff, if you look at the area of the graph, the buildings that we've been doing major repairs on are all pre-1989. So in that sort of smaller part of the graph, there's a whole building stock that's starting to turn 25, and it's getting older. So there's a huge amount of work to be done coming down the pipe, and we have to keep an eye on that stuff. Not only the stuff that's turning 25, but that older stuff where we're starting to run into problems which we really haven't seen as part of the mainstay of the building repairs. Like there's your roofing, there's plumbing work, there's boilers, all that sort of regular stuff. But then there's another realm and another whole, sort of a whole group of things that are going to need to be done to these older buildings. So just keep that in the back of your mind as we go through the presentation. So obviously, there are things that are very apparent. And you walk past a building like such as this, it's very apparent. But there's lots of stuff that's just not so apparent. And you might walk past a building, or you might have a building that looks just like this, and it's very easy to walk past an issue that could be systemic, and it could be happening throughout the building and actually leading to some pretty major problems. A couple of the deterioration mechanisms that we're going to be really focusing on today are corrosion and freeze thaw. There's obviously a whole slew of stuff and mechanisms in which a building or building components can fail and deteriorate, but we're going to focus on the first two, corrosion and freeze thaw. So, one of the premises and one of the things that you just have to keep in the back of your mind, I think everybody knows this, is that, steel rusts. I know it's not really terribly new to you, but it is a phenomenon that we have to deal with on a daily basis. And there's this whole chemical process that goes on, but basically you need iron, water, and oxygen to cause rust. I mean, that's going back to sort of high school chemistry, if you will. But in conjunction with just your normal rust, you can get very aggressive corrosion happening as well as soon as you introduce salt. And this is a great example this is taken from San Francisco on a pier that juts into the bay. And the extent of corrosion there is phenomenal. And the steel is rusting aggressively. It's caused the concrete to spall off. And I'm sure you're familiar with it to some degree. It's just a great photo that demonstrates that process. Another process that you might not be so familiar with is something called carbonation. And this is where carbon dioxide within our atmosphere can get into concrete and depacify the natural protective cover that concrete provides on steel and cause corrosion as well. Now that's a little bit more complicated. There's a lot of debate in the industry about how effective or how important this is and how relevant it is to the degree of corrosion. But our experience has obviously been that carbon dioxide is and does cause it does cause steel to become depacified in concrete. So what that means is that the steel within concrete is naturally protected. And so I don't know if most people know that, but the inherent alkalinity of the concrete protects the steel. As soon as you turn the alkalinity to more of an acidic environment, which carbon dioxide does, it corrodes. It causes the embedded steel to corrode. That's a very important phenomenon that we need to be aware of. And one of the results of corrosion is obviously a loss of structural capacity. You're starting to lose section loss. But another interesting fact is that steel expands, and it increases in volume by about 10 times. And that expansive, that rust formation, as it's growing, it can impart loads on the structure that were totally not intended. The engineers are not designing for steel that's going to corrode. They're designing for the steel as if it's going to be maintained. So it can have all sorts of effects on the building structure. And then freeze-thaw action. In this environment, northern American environment, we have freezing temperatures, we have warm temperatures, and that constant freeze-thaw cycle leads to some fairly significant deterioration. And, we've all seen some brick spalling, there's some mortar joint deterioration there as well. And so it becomes very important to manage water on our building envelope. So that's just trying to give you a little bit of a backdrop so that we can move into some examples now to show you some specifics on some buildings that I've had the opportunity of working on. So the first example here is a 1980s multi-res building, and no indications of water leakage on the interior. Nothing more than the staining that can be seen at the floor slab levels. And this is actually rust staining coming out from the floor slabs. And very easy to walk past this. And I guess subsequent to a review, it was recommended to do some further investigation and to do some openings in the walls. And so what you find after doing some openings is that the embedded steel shelf angles are in fact corroded, and they're corroded to the point where they are starting to lose structural capacity. And if I just go back to this photo, the design of this wall structure is such that these panels are supposed to be individually supported. So each brick panel is supposed to be supported by a shelf angle, and then the next panel down is supported by a shelf angle, and the next panel down is supported by a shelf angle. But as soon as you start to lose structural load-bearing capacity on those shelf angles, all of these bricks start to load up and stack. And so all of a sudden you get unintended loads coming down. So all the loads that are being taken by this bottom panel are all of a sudden significantly increased, because now it's starting to support loads from upper panels. And so it's very important to make sure that doesn't happen. If you start to get those stacking effects or loads being compounded within your wall assembly, you will have other issues such as cracking, spalling. You can have brick panels that start to bow and come loose. And so it's important to get that looked at. I just got a slightly better picture of the amount of corrosion that's happening within this wall assembly, and it is fairly significant. So,
what's the solution there for that building?
Well, the first thing to do is to check to see whether there's a stacking effect going on with the brick panels. And if that's the case, then you have to be very careful in relieving those loads. So you want to return the loads back to the shelf angles. And in order to do that, in some cases, you'll have to replace shelf angles. And in some cases, if the corrosion is not that bad, if there's still enough structural strength within the shelf angle, that can be cleaned. So it can be cleaned.
Ultimately, those walls are designed for water to get past the brick, so you want to provide a mechanism for that water to get out. At the bottom, you want to protect that shelf angle and allow the water to get out, instead of sitting on the steel shelf angle and corroding.
But if they're corroded past their structure,
You're going to have to replace them.
capacity, you have to replace them?
Yeah.
And
You do it in sections, yes, and you shore up the panel.
I'll add, it's an expensive process. We have one in Halifax that's underway, I guess starting in a couple of years, and it's about $400,000 to do all the shelf angles for the whole building. So quite an expensive process.
You start at the top and you work your way down. You start relieving the load on the bottom panels.
Is that a common design practice to have various shelf angles at story intervals, or is it just because the shelf angles can only support a certain amount of weight from the bricks, so they break it up into those levels?
There are designs where the shelf angle is supporting more than one story of brick. The more common one that we see is the brick is actually supported on the floor slab edge. So it's sitting right on the extension of the floor slab. In these cases, it's the steel shelf angle.
Good. Okay, let's move on to a second example here. This is a 1960s multi-res building. Similar situation where there's no really apparent issues. You know, walking around the outside of the building, you really don't see a lot. There's one brick spall. There's no reports of leakage. And you know, when you start to take a closer look and you look at the upper floors in this is the same building, there's rust jacking going on. So as I said, when steel corrodes, it expands in volume, and it can cause a jacking effect. So it's imparting a load, an expansive load. In this case, there's a shelf angle running along here, and it is corroded to the point where it is jacking up the walls above it. And so it's a similar situation where it needs to be, this hasn't been opened up and investigated as yet, but it definitely, there's something going on that's concealed there. It needs to be opened up, check the load, check the condition of the steel shelf angle, and then make a determination on what the repair is going to be, whether the shelf angle can be cleaned. In this case, I doubt it. It's probably going to need to be replaced. But also there's going to be some significant brick removal needed to access that shelf angle and to restore that wall back to a vertical plane. So and this is another example of an elevation on the same building, and it's just a different wall area, but similar. Water is obviously getting into these shelf angles and causing them to corrode. So this is taken with a zoom lens, and from grade, this actually was more apparent than the other shot that I just showed. But keeping an eye out for this sort of vertical differential movement, you can see that there's a gap forming just above like where the shelf angle is. So that's an indication that we're getting some rust jacking going on at this building. And this is a shelf angle on the lower floors where I was able to measure some of the rust jacking going on. So you can see there's about a ½ an inch or about 12 millimeters of rust that's formed on the top surface of that shelf angle. And so with 12 millimeters, if you use a 1 to 10 factor, there's approximately 1 millimeter loss of section estimated on that shelf angle, right? So that 1 millimeter of the top surface of the steel of the shelf angle has expanded in volume to about 10 times. And you can see it. So that whole chunk of rust that's forming on top, that's the volume increase of about 1 millimeter of steel. It's pretty incredible. Like, it's really neat how it grows in size like that. All right, let's move into a garage example and a phenomenon called punching shear. So when we're looking at garages, we're paying particular attention to older garages and which have a construction where there are no column capitals and no drop panels installed. So you'll notice that the column in this situation comes straight up and meets into the slab. That's an older design. Typically, you won't see that type of design in newer construction. And we have bars, we have top steel, and then we have bottom steel and slab. And obviously we have some cars parking on it here. So what we're worried about, or what's of concern, is making sure that the steel right at the column and the top surface is intact and in good shape, because that's providing a large amount of the structural load carrying capacity of the slab. And so what we're concerned about is getting a cracking phenomenon. If we start to lose capacity between that top steel and the concrete surrounding it, I've got another slide here. So if you start to get concrete delaminations in this area, you start to lose structural capacity very quickly. And this can lead to a phenomenon called punching shear, where the slab will not fail slowly, but it will fail abruptly and suddenly. And I think you've probably seen some of these cases where we have had some garage slab collapses, and this is a garage that was in Windsor that collapsed. I think it was this was in 2010, I believe. And so as you can see, there's obviously cars parked on this roof slab. What you will notice is that the columns remain vertical, and the slab has, if you will, what it's called punching shear, because the column effectively has sort of punched through the slab. And that's why it's known as punching shear. But this needs to be carefully evaluated. Older garages where there's potential for concrete delaminations, corrosion, especially on roof slabs or parking decks. Not roof slabs with landscaped areas, they're of much lower risk, in the case where they haven't increased the overburden over the years. But where you have a potential for corrosion right around the column to slab interface, it has to be checked on a regular basis. You have to understand the construction, and you have to understand the risk. And so
you get very little warning with punching shear. There's not a lot of evidence. The only evidence you do see is the cracking on the top surface. And unfortunately, in most cases, the top surface is covered with some sort of waterproofing or asphalt surface that the cars are parking on. So you will not see that cracking.
Would you see it from the other side though?
No, because most of the cracking is on the top side. If it's gotten to the underside, you're very far gone.
Okay, example number 4. I've got to get hustling here. So, anybody recognize the Algo Center Mall? Another corrosion issue. So if anybody's read the commissioner's report, phenomenal amount of work went into investigating the cause of the collapse and all the investigation work that happened leading up to it. And it's amazing how many engineers were involved, how many contractors were involved, how many owners were involved, and so forth and so forth. But really, this is a case where there was obvious leakage, there were obvious problems on the inside of the building that were just ignored for years and years and years. And there wasn't an adequate amount of attention put on the concealed deterioration that was going on. They could address things like manage the water on the interior, not well, but they were able to capture it and direct it into buckets. All sorts of neat photos. But at the end of the day, it did lead to a collapse. And unfortunately, this beam that you see lying across the big opening here was the main culprit. And the connection where that beam interfaced with a column was the main source of the failure. And it was just corrosion. It was as simple as a parking roof deck, cars, bringing in road salt, leakage over a course of multiple years. There's debate and arguments over whether the design was inherently flawed, but regardless of that, there was ongoing concealed corrosion for decades, and it resulted in a massive failure. And so it's something that could have easily been prevented. And this is a shot from the bracket, or a similar, this is an adjacent bracket, I believe, between a beam to column interface, and they associated the amount of corrosion with similar to a marine environment. They said it was just phenomenal how much corrosion was there. So, really unfortunate circumstance. Okay, let's move on to something a little bit different. There's something called Kitec piping in the industry, which we're starting to see in newer construction. You're not going to see it in the 1970s and 80s buildings, but because it was sold between about 1995 and 2007. And so PEX piping is a form of PEX piping, but it has an aluminum core. So if you look at the cross-section of the pipe, there's an aluminum core in the middle embedded between the PEX. And you can also identify it by the stamps on the fittings where it says Kitec. And the problem with Kitec is that there's a class action lawsuit out against Kitec. Because there's a problem with the fittings. There's the interaction between the aluminum between the PEX and the zinc, the fittings which contain a high content of zinc, cause something called dezincification. and that results in a product being formed within the pipe, and expansive, another one of these expansive things, unintended consequence that forms, and it causes bursting of the pipe. And so you just can't predict that it's going to happen. It's not that old. It was only sold between 95 and 2007. There was a class action lawsuit that was settled, and there's a fund available for anybody that has Kitec and decides to change the piping within their building. So what we're seeing now is a slew of primarily condos that were built with this piping and going through a process of having to replace it. And they're replacing it mainly for insurance reasons, because once they get a leak, the insurance companies are saying, hey, we're not going to insure you because we know you have a problem. The industry knows it's a problem. You know you have a problem. And so we're going to force you to, we're not going to insure you, actually, if you maintain this piping. And so it's become a big issue. It's becoming a bigger and bigger issue in the marketplace. It's primarily focused on condos right now. But if you are looking at any new developments, or you have some new developments within your portfolio for multi-res, this is something that you want to definitely be aware of. So we'll go back into another wall example here, and this is an example of sheared header breaks. And a header break is, I'm going to have to blow through some of these here. A header break is where they're using the face brick, turning every 6 courses at 90 degrees to connect back in, to provide a lateral connection of the face brick with the backup concrete block wall. So this is what forms your wall structure. It's a combination of the face brick and the concrete block backup. And by turning the outside face brick and embedding it in the backup wall, which you can see in this photo here, you can see the red bricks, how they're tied into the concrete block. And on the outside, this is what you see. You just see a row of bricks which are turned on end. That's what forms the connection and basically combines to form a monolithic wall structure. No longer used. There are inherent problems with the design, but you still find it in older buildings, sort of 1970s vintage, but not typically later than that. So here's an example of a building on Eglinton where you'd look up, this is the north side of the elevation, you look up at this wall assembly and you really don't see much going on. But over the years you get shrinkage of the concrete frame, which imparts stresses on those headers, and it causes them to shear. And so as the frame of the building shrinks, and it's a very, very slow, small process that happens, you get differential movement between the face brick and the block. And because the bricks are not strong in shear, they just shear. So it looks like they look good. So looking at the bricks from the outside, you know what? They look fine. But there's no way of telling whether these header bricks are intact and remain so. And this is the building on Eglinton, which had, I guess it's 4 panels fall off. And this was this was earlier this year. This was about 2 or 3 months ago. It hit the news. So again, you need to be aware. It's definitely an invisible issue. It's something that, inherent to this type of construction. If you have it, it should be monitored and investigated. You have to do some openings to see if those header bricks are still intact. Today, in more modern construction, the lateral connection is provided with a little piece of metal, which is flexible, so it can absorb some vertical movement, and it still provides that lateral securement, which is critical. So. I'm not trying to show you really sort of the detriment or these extreme examples, but it just gets the point across. I hope I'm not coming across as showing all the bad stuff. But these are the risks, and again, just keep in mind the building stock that we have in Canada is getting older. We have a lot of these older buildings, a lot of these issues. As long as they're continuously reviewed, maintained, and understood, they can be managed. There are ways of managing this type of construction. So we're going to move in. Have I still got time to continue going through here, Martin? 5 minutes. 5 minutes? Okay. Here's an example of some poor workmanship. So as you can tell, this is a newer building. And so newer construction. And looking at it, even looking up closely at the sealant work, you know what? It looks pretty good. You look at it, it's intact, it's got a nice profile. But when you look at it a little bit closer and you start to stick your finger into it, you realize that it's not very well installed. And I've run across a number of buildings now where this is the case, and the sealant is just barely bonded onto the window frames by probably a millimeter or two. It's just very, very minimal. And so it's easy to walk past something like that. You're going to look at it, you'll walk around, look at the windows, new application, it's new installation, you think, wow, this is great. This looks really good. Stick your finger in it, and lo and behold, very little bond onto the substrate, and there's really very little material. I'm not even sure how they applied it with nothing behind. I don't know why there's a big gap behind the window frame as well. But obviously this is not right, and this is an example of just poor workmanship. So looking at a proper detail, there should be a minimum of 9 millimeters of bond. So we're looking at a sealant profile that's got maybe 2 millimeters, and the 9 millimeters is sort of the minimum. So it's really short. You're not going to see a typical service life out of that sealant. It's not going to last 15 to 20 years as it should. We've seen buildings where it's led to systemic sort of chronic leakage within 5 years. And so this is a common issue in the new construction. And just an example of some new sealant being applied and doing a pull test on it to check the bond, make sure that it's being installed properly, the profile is correct, there's enough material installed. So it's easy for a contractor to put a lot less material. It's going to save a lot of money, really, and time. So back to this fancy building here. Another example where easy to walk past. There were some indications of some water leakage on the interior, and in this case, I'll go through what resulted. This has wallpaper on the outside walls, and as soon as you start to peel up the wallpaper, that's mold. Within the wall assembly, there's mold on the back face of the drywall here, and they are getting leakage. But it's been ongoing for a long time, and this isn't just in one unit. This is something it's throughout. It's a systemic issue. It's throughout the building. There's some systemic issues with the window construction and age, and also with the sleeves for those for the PTAC units. And then within the wall assemblies as well, there's corrosion. In this case, this is a steel stud backup. So the other wall we were talking about had a concrete block backup. A lot of buildings built sort of starting in the 80s, they built with steel stud backup and drywall interface, and then an airspace, and then the brick veneer. And so buildings in the 80s were known for this sort of new construction technique, and they were not well designed. The outer gypsum board was paper-faced. It's prone to getting wet. And as soon as gypsum board gets wet, it just starts to turn to mush. And it's also prone to mold. The steel studs, if they get wet, they tend to corrode out. They are a structural element to the wall. So as soon as they start to corrode, you lose that lateral support again. You're losing support for your bricks. You're losing that lateral support for the whole wall assembly. And so it turns into a much, much bigger issue very quickly. But this is all kind of concealed. It's tucked in the walls. When you have steel stud backup wall construction in your buildings, we always recommend doing some periodic testing to do some openings, check the conditions. Areas that are particularly problematic are around window corners. And as you can see in this first photo here, there are little foam gaskets that they use to make the joint between the horizontal sill and the vertical mullion of the window. And those fail after a while. So after 20 years of service, water that comes into the sill that's intended to drain out is getting caught in that corner, and it's going through the corners of the window frames, and it's going right into the wall assembly, like right in there.
Yeah, about 1 minute left.
Okay, I got to go. Okay. Let's just maybe, I'm almost done actually. This is a transformer in southwest Ontario where the door blew clean off the unit. I don't have a picture of it being blown off, but an inspection report revealed that it hadn't been inspected in a while. There's some heaters inside it which were disconnected. There's mouse nests in there. There's water in the unit. It's just a matter of it hasn't been inspected in a long time, but they're prone to issues, and so got to make sure that they're opened up, serviced, cleaned, inspected. It's part of just a regular routine maintenance thing. But that door blew right off the unit, shut down the entire building for a few days. So, okay. Now, preventive, a little bit of, on the preventive side, if I've got a minute or so, I would say one of the number one things is water management. Have a look around your buildings. Like, just take a walk around. And, I was at this property, and I love this photo because it just rained the night before. And you can see the difference of where there's a slight overhang on this side of the wall. There's no overhang here. There's no drip edge on this little cornice detail. And this wall is obviously getting really, really wet. And this is just detailing. And, if there was a proper drip flashing, something to get the water and kick it out away from the walls, these guys are going to save themselves a lot of headaches down the line. You just got to get the water off the walls. Like, you don't want water. The masonry is designed to get wet. It can absorb some water. It's designed to do that, but you want to kick as much water away from the walls as possible. It's going to save you a lot of time. And there's a great little study that was done by Building Science Labs. It talks about the effectiveness of drip edges, and even, believe it or not, there are actually different performance based on a different profiling of a drip edge. I mean, I'd be happy just to see any drip edge, but you can actually get better performance depending on how you design it. And so think about doing a walk around your properties, after a rainfall, during a rainfall, and see how is water hitting the walls. How is it getting kicked away? Where is it going? What's going on? It's really powerful. Intrusive testing is going to be a must. It's just going to be part of our norm. And in this case, you can see a concrete slab that sounds great. It looks great. The mastic is in great shape. As soon as you do a core, there's clearly a concrete delamination buried beneath the top surface that you won't be able to detect. You may not detect that with a chain drag survey or a hammer. In some cases, you just got to get in there. You got to do some openings, do some coring, and try and identify those concealed conditions. And it's a matter of understanding the construction, understanding the risks, and determining an appropriate review plan. So I think that's it, Martin.
Thanks. John has asked me to make a few comments, to summarize some of the stuff from a landlord perspective, because Realstar manages about 200 buildings across the country, and we deal with a lot of these problems on a day-to-day and on a yearly basis as well. We haven't done any pipelining yet. That's something we are studying right now, so it's sort of a good time to have the presentation, and I'll be talking with Mark after as well. But one other thing that's sort of to add to what Mark talked about was it's even more economic if you have a situation where you have asbestos in a building, and the alternative that we have been using in the past is changing the pipes. But when there's asbestos that you have to deal with, that of course raises the cost by 2 or 3 times. So that makes it even more economic to do the pipelining. And sort of the environmental issue is one that wasn't really dealt with by Sean and Sam either. But that's one that we deal with quite a lot. When water gets into building, you have the mold growing, very high cost. Really a lot of problems that flow from that. Similarly with asbestos damage, water gets in there, you get, the asbestos is damaged, and you spend a lot of money to remediate that problem. We haven't had any of the major failures that Sean was talking about, similar to the Algo Mall or the one in Windsor. But certainly we have a lot of issues in buildings. We're picking up buildings all the time that have possibly managed by someone else in the past, not as well. We come in and then we have to shore up a building on an interim basis. We have to put on a support to the wall, to the facade, to keep it in place while we do more a permanent solution. In the province of Quebec, they've recently brought in new regulations, and over there you have to have an engineer review both all the parking garages as well as the facades of the building, and every 5 years you need to get a study done. And that seems to me to be a prudent time frame to look at these things. Like, we generally get a BCE, so a building condition survey, done every 3 to 5 years at all of our buildings across the country, and it brings up a lot of issues, not only the ones that we've talked about today, but other issues as well, and we use that then for our capital planning. And I certainly agree with the comments from everyone today that you're a lot better off dealing with these things on a proactive basis rather than a reactive basis. If you're dealing with, some of these major structural issues on a proactive basis, the cost is going to be 10, 20, maybe up to $100,000. But if you deal with them after they've gone too far, you can look at hundreds of thousands up to, we spend millions of dollars on some issues in buildings. So with that, I will throw it open for some questions from the audience, if you have any.
Well, you got to start off with understanding the construction. So pull out the AC unit and understand the sleeve. Quite often we see that the sleeve is supposed. So there's a sleeve that goes through the brick wall, and then your AC unit goes into the sleeve. And so condensate from the AC unit drips into the sleeve, and it's supposed to hit the sleeve and then drip and then be evacuated from the opening. Quite often those sleeves, the joints, open up over time. So they need to be resealed, and often the sleeves are sloped the wrong way. They're supposed to be sloped outside of the building, and they're not always sloped. Sometimes they're flat, or sometimes they even slope into the building. And so it's a matter of getting in there, opening it up, and that can be corrected by resloping or resealing.
So do you go back to the existing wall system? Is there a quick fix solution to seal them up so that they're not a thermal bridge?
Oh, are these ones which have been capped off? These are.
Yeah, that's what I'm talking about, where I want to cap them off and get rid of them, but without having to rip the sleeve out and actually put in brick and then put into the water, glue seam or something like that.
Right. Oh, well, quick fix. I don't know. Maybe Sam.
Insulated panel of some sort.
Yeah, you got to be really careful, because if your drainage plane is actually behind the bricks, then by face sealing the whole outside, you're not solving a problem. You're going to be creating a bigger problem. So you have to understand what the wall construction is. Is it veneer? Is it solid masonry construction? Understanding, what's the risk of water getting behind the first layer of brick?
You've got to drain that water. You've got to design
we
something.
don't want to use them as air conditioning. We want to
No, I got you, but you can't just face seal it.
You can't just fill that void with some sort of expandable foam that acts as a vapor barrier.
Not without really understanding the wall construction first. Yeah, that might be a solution. If it's solid masonry construction and there's very little risk of water getting in behind. But if it's a veneer construction, I think you'd want to be more careful than that, yeah.
Any other questions? Yeah, sir.
The fact that you mentioned the PICs and the aluminum and the new PICs, they don't have anything in it. It's pure plastic.
That's right. Yeah, there's no aluminum core. So if you feel a piece of Kitec piping, it's rigid. So it's very hard to bend it. The PEX that you more commonly see was very flexible. It just coils easily. But with the aluminum core, it's almost like a pipe. You do have to use some effort to bend it. So it's one way of finding. It's clearly stamped. I kind of blew through the pictures, but it will be clearly stamped. It's an IPEX product. So the stamping is IPEX, but the key is on the fittings. It says Kitec, Kitec.
I have a question for Mark. So to run through what the residents notice as you go through one of these programs, so the inconvenience of any to the resident. And the second question is there times when this solution doesn't work in piping?
There are times where it doesn't work, is when there is galvanized pipes, like I explained earlier. And in very rare cases, the erosion is at a point where the pipe is paper thin, literally paper thin. That's when we suggest to repipe a building, and that's when we can't touch it, just because it would blow apart by the pressure that we apply to the system. And the inconvenience for residents is very minimal. During the process, per riser, we have to go into a unit 5 times throughout the day for less than a minute. We're just installing a device, and then with a valve that lets us control air. And we have to go 3 times a day. We have to go to control that the air. And then the 5th time, at the end of the day, we take the device back out, put everything back to normal, and that's it. So there is really no intrusion. There is no inconvenience or little inconvenience to the residents. other than there is no water for 26 hours. In that one riser, of course, we'll always make sure that there is one source of water. If we're working on the bathroom, there will be water in the kitchen and vice versa.
Any other questions, sir?
One more question on piping. I don't know which one of you will answer. When you have risers, and over the years you get deposits in the risers and get clogged up halfway or quarter way. So these pipes, are we talking about all the risers? What's the best solution?
Well, if you're getting a clogging issue, it's probably a galvanized steel riser that you're talking about. Is that fair?
It's never clogged completely, but
Yeah.
you can see that the pressure in the building is changing from top floor to the one floor below or one floor.
So that's galvanized steel, and what Mark was saying is basically with galvanized steel, it's a replace. That's your option. Galvanized steel, it doesn't make any sense to try and clean it and salvage it. You need to just replace it. You can do it in a piecemeal fashion, or you can do a full riser replacement program.
I want to thank the panel for their very interesting presentations and responses to the questions today. CFA always wants you to fill out your comment forms, so I would ask that you do that. You now have a break until 10:15 when the next sessions take, so about 30 minutes. You have coffee available. They're asking that you go out that door. I'm not sure what's over there, but John asked me to have everyone go out that door instead. And please take the opportunity to go meet with the different exhibitors that are here who are generously sponsoring the session today. Thanks very much for attending.
Good luck.
The RHB Insider Network is an RHB Inc. production. Publishers of RHB Magazine and the producers of RHB Newsreel.